In this last part of the class, we're going to try and develop some techniques to further increase the library of integrands that we're actually able to integrate. And today we're going to talk about an extremely important formula called integration by parts. Now, this formula has a special place in my heart. When I was in graduate school, I was taking an applied mathematics class, and we would use integration by parts so often that it became a joke. It became a meme. A professor would always say, "The bell rings, you salivate, and you integrate by parts," because it was a conditioned response. You just did it every single time. No matter what problem you were working on, odds were good you were going to have to use this technique as part of the problem. So here's the idea. Suppose that we have two functions of x, and you can call them f of x, g of x, but to keep things really short, to keep things really simple, we're going to call the functions u and v, holding with tradition. Now, do you remember, product rule, how do you take the derivative of the product of u and v? We take it by taking u prime times v, and then adding that u times v prime. Two factors becomes two terms, each term getting one derivative on a function. Now suppose that I went backward and I decided to take this expression and I wanted to integrate both sides with respect to x. Well, the fundamental theorem of calculus says that if you integrate a derivative, or if you take a derivative of an integral, those two actions cancel each other out. And as a result, uv prime has canceled integral. Uv is equal to the integral of u prime v with respect to x plus the integral of uv prime with respect to x. Now I can rearrange this ever so slightly by subtracting one of these integrals to the other side. And I can say this, and here is the big takeaway. Here's the integration by parts formula. Suppose that you're trying to take the integral of two functions multiplied together. Call one of them u prime and call one of them v. If you can roll backward and you can find out the antiderivative of u prime, called u, and if you roll backward and find the derivative of v, then you can fill in all the blanks in the expression on the right, and maybe it will be easier to calculate the value of the expression on the right than it was to calculate the value of the expression on the left. Now we have done this in the case of an indefinite integral, and this works just as well for a definite integral. If you want to integrate from a to b, you can still do uv evaluated from a to b, and you can still do the integral of uv prime integrated from a to b. Now, this may not look that great in the beginning, but let's see how it can be useful in the following exercise. To integrate a product, x times cosine of x. Integrate this product. Now, you can try all manner of substitution, u substitution here, but no u substitution is going to be able to simplify this to the extent that you need. So instead, I'm going to try a different tactic. I'm going to think about this as u prime times v. I'm going to think about v as being x. I'm going to think about u prime as being cosine x. Now if I do that, if I think about v as x and u prime as cosine x, then I can find v prime, and that's just 1. And I can take the antiderivative of cosine, and I can find u, which would be sine if u prime is equal to cosine. So, if I think of this one on the left as v times u prime, let me go to the other side of the integration by parts formula, replace u and v prime with their respective sine, 1, and cosine, and let's see if the expression on the right is any easier to work with. Okay, u times v. U times v is x times sine x. U times v is x times sine x. U times v prime, the integral in the back. U is equal to sine x, and v prime is equal to 1. Because v prime was such a simple function compared to u prime, I arrive at an integral that actually is very easy to take. I can take the antiderivative of sine of x, and the result is just negative cosine x. So here is the upshot of integration by parts. I can essentially move the derivative in this product. Think about cosine as the derivative of sine, and move the derivative so that it's not being applied to sine. Move the derivative so that it's being applied to x instead, because the derivative of x is extremely simple, it's just 1. By moving that derivative to the other factor, instead of the one that you originally had, you can get an integrand that is much, much easier to work with.